Yeah, hello. Yes. Uh, if I'm audible, please let me know. Yeah, okay. Thank you. So I guess there will be some lagging, maybe for maybe few seconds, 5 to 10 seconds. There will be lag. So yeah. So we'll wait for a few minutes and then we'll start the problems. Yeah, since some of you told that they don't know Hindi, so I'll avoid talking in Hindi. But if you feel problem like while understanding any solution, then please let me know. I'll explain you in Hindi as well. Okay, so you all are from MSc or you are in BSc or you can see Rohit, Chinmay, Sachin. So you guys are from MSc? Yeah, Manmohan, good afternoon. Okay, so so Devasis, you are from MSc. Okay, Manmohan, you are also from MSc. Chinmay is also from integrated 5 year MSc. So Rohit is also from MSc. So most of them are from MSc. Yeah, yeah. Okay, so yeah, we will wait just for 1 minute and we'll then start. So if you feel any problem, just let me know. I'll try to see the chat box in the meanwhile. Like I have switched on my phone so I can see there probably. Okay, so I am Sachidanand. Currently, I'm a postdoctoral fellow at ICTS. So it stands for International Center for Theoretical Science, and it comes under TIFR. And yeah, I completed my PhD recently from ISER Kolkata. Yeah, so the thing is that I completed my PhD in just last year, 2022 only. In December 2022, I completed my PhD, and joined here as a postdoctoral fellow. So yeah, some of like I was just talking to some of my juniors back there, and they suggested me or they asked me like if I can keep some sessions on CSIR NET as this is like it will be in June, I guess. I don't know exactly when it will be, but somebody told me that it will be in this upcoming June. So I hope this set of sessions will be helpful for all of you. Though, so the plan is, so let me just, yeah. So the plan is like, yeah, so, uh, just a minute. Yeah, yeah. So the plan is like I'll give two sessions, one on Saturday and one on Sunday. And this was the only session that I gave on Wednesday because this Saturday I'll not be there. So from next week, so next session will be on this Sunday, and from next week onward, we'll have a session on Saturday and on Sunday. What we're going to cover is in the first two or three sessions we'll be cover linear algebra, and next two or three sessions we'll be covering real analysis, and then I'll see after that. I don't know if I'll be there. Then we will be discussing on abstract algebra and complex analysis. And my plan is to solve the last year problems. So I'll start from the very recent February 2022, and we'll try to cover at least last 2 to 3 years problem. Okay. So, yeah, why I choose real analysis and linear algebra? Because I saw from last few years paper, and it seems that in both of these uh, fields, you will get uh, like problems worth around 45 to 70 or 40 to 70. So minimum marks is about 45 to 40, and maximum is about 70 to 75. So so in a way that if you can learn or if you can grasp linear algebra and real analysis in a good way, then that will be help you to boost a good score in CSR net. And then we will try to cover abstract algebra and complex analysis, even topology also. Okay. So yeah, so in like for example in February 2022, there were there were like 6 problems from section B, part B, and 7 problems from part C. And part B contains like 3 marks, and this contains 4.7 marks, and the like total was around 51.25. And even in June 2022, it was 56 in total. So it's like you will be getting around 50 marks each year on an average. And that's a good marks because if you score around 50 in linear algebra and around 50 in real analysis, then that's a very good mark in CSIR net because then then the probability of you getting selected is higher and higher. Okay, so what we will do is like as I told, I'll be discussing problems from February 2022. So let's see. So yeah, yeah. So if you have any problem while understanding, please leave a message on the chat box. I'm seeing it. Okay. So the first problem, so it might be like the ordering, I don't know. I took it from here and there sources. So I don't know what is the numbering, but this is the problem. So the problem is like consider two statements given below. And the first statement is there exists a matrix N in M4R. So N is a 4 cross 4 matrix. I guess, Yashoda, you can do the, just let me see. Yeah, you can do the this the 720 or 1080. You can choose because from my end it is fine because I am seeing it from my phone and I can see a good quality. So is the video quality like blur for everyone or it's okay for rest of them? And can anyone, if anyone, let me know? I'll just check once. Yeah, because I haven't done any live, so I don't have much like idea about this live sessions and so on. So let me just see. Yeah, it is. Yeah, it's fine. Okay. Yeah, thank you for confirming. Okay. Yeah, you can select the 1080 or 720. Okay. So the first problem is consider the two statements given below. The first statement is there exists a matrix n in n4R in M4R. That means that n is a 4 cross 4 matrix such that these two vectors are basis of a row and this is in the null space of n. Okay, so yeah, so what is the plan is like I'll after each problem I'll give you a few minutes, for example, 2 to 3 minutes to think about the problem. And if you have the answer, you can write it the like correct option, and then we can discuss the solution so that it will boost your thinking capability as well. So the first option is the first statement is this, and the second statement is that there exists a matrix M such that this is a basis of column, and it is given that this is in the null of n. Okay, and you have to see that which of the statement are true and which of them are false. Yeah, so I'll wait for a few minutes, and you can try in the meanwhile. Just for a hint is like you can use rank nullity theorem as well here. And there are many ways to solve this problem. And if you have some like, for example, if I'll tell a method to solve it, and if you have some other method, then also you can share with us so that we all can know a different method. So anybody got the answer at least? Like which of them is false at least? Okay, so let's see. See, what is the first thing? First statement that there exists a matrix n such that this is a basis of row of n and this is in the null of n. Okay, fine. So what I will do, so I'll just write the matrix A as so. So these two vectors are given in the basis of row vector. So I'll just write these two vectors in the row that 1 1 1 minus 1 and 1 minus 1 1 and 1. Okay, and the rest of this, so if this is my row 1 and this is my row 2, so these two will be linearly dependent on row 1 and row 2. Yeah, Manmohan, you are right, one is false. Yeah, so row 1 and row 2, so the rest of the two rows are linearly dependent, so it's like alpha r1 plus, sorry, alpha r1 plus beta r2, and this is something a r1 plus b r2. Okay, so this is the matrix that A will look like. It is not necessary that here it's 1 1 1 minus 1, but it is the linear combination, linear multiples of this. And if you now it is given that this vector 1 2 1 4 is in the null, so if I'll take 1 2 1 4, then the output should be, because this is a null vector, this is in the nullity, then the output should be 0 0 0 0. Okay, but what if you compute this multiplication? See, here we will be getting in the first will be 1 plus 2 plus 1 minus 4, which is 0. So this is fine. But if you compute the second entry, that is 1 minus 2 plus 1 plus 4, and this is not equals to 0. Okay, and hence this is not equals to 0. And therefore, this vector is not in the null space. And hence this matrix, like such a matrix where these two are the basis of the row and this is in the null, cannot be possible. Okay, because we have constructed the matrix, but we see that the given vector is not in the null, and hence this statement is false. Now for the second statement, it says that there exists a matrix M in M4R such that this is a basis of column of M and this is in the null. So again, the method will be same. Now instead of writing the row vectors, what I will do, we will write in the columns. So let's write. So now this is the matrix M. So let's write. So my M equals to, yeah, I just write. So the column will be 1, 1, 1, 0, 1, 1, 1, 0, and 1, 0, 1, 1. Okay. And the other two columns will be linearly dependent on this. So I'll just write the other two columns. So if I'll write this is as let's write as, so this column will be as a linear combination of these two columns. I'll just write alpha plus beta, and then alpha, then again alpha plus beta and beta. And the fourth column will also be in the linear, I can write as the linear combination. So it will be A plus B, then A plus B, and then B. Okay. So this is the matrix. And now it is given that the two vectors, that 1, 1, 1, 1, this is in the null space. So this is 0. And the second is 1, 0, 1, 0. This is also in the null space. Okay. So what I will do, I'll solve this equation to see whether I can find the value of alpha, beta, A and B. Okay. So if you see, so let's see, just add after, yeah. So if I'll just see, so what is the thing? So I'll be getting 2 plus alpha plus beta plus A plus B, and this is my 1 plus alpha plus A, 2 plus alpha plus beta plus A plus B, and the last will be 1 plus beta plus B. And this is this multiplication, and this has to be equals to 0, 0, 0, 0. And similarly, if I'll multiply this, so let's write that also. So that will be what? It's like 1 plus alpha plus beta, and then second will be 1 plus alpha, third will be again 1 plus alpha plus beta, and last will be beta. And this is equals to 0, 0, 0, 0. Okay. So now you see that we have two set of equations, and we can just solve this. So from this, what I'll be getting, beta equals to 0. Okay, just take, yeah. And if beta equals to 0, and from this, what is 1 plus alpha plus beta is also 0, and 1 plus alpha is equals to 0, so alpha is equals to minus 1. So I'm getting alpha equals to minus 1 and beta equals to 0. Okay. And if I'll put it here, and you can solve it for A and B. So I'll just leave it to you to check that you can find A and B so that it has a solution. And hence this statement is true. Yeah, but there is one another method, and that's simpler than this. It has some calculation, but the another method does not involve any calculation. So let's see that. See, so what is given that the two vectors this. So I'll name these two vector as this is let's say v1 and this is let's say v2. Okay. So what I have to construct, I have to see whether there exists a matrix M such that these two are in the basis of the column and these two are in the null of n. So what I will do, I'll take M of E1 equals to V1, M of E2 equals to V2, and then rest of the two vectors which are in the null. So it's like 1, 1, 1, 1. This will be go to 0, and M of 1, 0, 1, 0. This will also go to 0. So I have to find, or I have to see whether there exists a linear transformation M which sends E1 to V1. So E1 is my 1, 0, 0, 0, and E2 to V2, and of course these two are given. So these two you cannot choose. These two you can take anything. Like you can, I chose E1, E2. You can take some other vectors. For example, even V1, V2 also you can take. So E1 is this and E2 is this, and now I ask that whether such a linear transformation exists or not. Okay, but if I write down the matrix of such a linear transformation, so see, so what is this? It's just V1 is 1, 1, 1, minus 1, then 1, minus 1, 1, 1, and here it will be, since it's 0, because it's this, so I'll be getting, right, sorry. Yeah. So let me, this, yeah. So I'll just write a statement here because then that will be easier to follow. So M is a linear transformation from R4 to R4, which sends E1 to V1, E2 to V2, and let's say this is my some two vectors, V3, V4, V3 to 0, and V4 to 0. Yeah. So these are like this, and we asked that does there exist such linear transformation? So we asked that does there exist such linear transformation which sends E1 to V1, E2 to V2, E3, V3 to 0, and V4 to 0. So when such a linear transformation exists, so if E1, E2, V3, V4 are linearly independent, we know that if that's linearly independent, then such a linear transformation will always exist. So we just have to check whether 1, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 1, and 1, 0, 1, 0, whether this is linearly independent or not. Okay, because if and hence and that's equivalent to whether the determinant is 0 or not. Sorry, determinant is non-zero or not. So if the determinant of this matrix is non-zero, then I can say that these all are linearly independent, and hence we know that this matrix will corresponds to that. So of course this is linearly independent because I'll just take one, and this the determinant is what? Determinant is non-zero. Determinant is non-zero, and hence these four are linearly independent, and therefore I'll get such M which satisfies this property, and therefore this option is, sorry, this option is true. Okay, and hence what is the correct answer? That sorry, 1 is false and 2 is true. Okay, okay. So I hope this is clear. If you have any question, then you can write in the comment. Okay, then let's proceed to the second problem. Yeah. So let A be a 4 cross 4 real matrix such that these 4 are its eigenvalues. And B is A to the power 4 minus 5A square plus 5I. Then what is the trace of A plus B? Yeah, so uh, I pause for 2 to 3 minutes. You can try, and if you get the solution, just you can write down the your correct options. Yeah. So did anybody got it? Or so yeah. So I'll just see. So see, A is a 4 cross 4 matrix and all the eigenvalues of A are given. And we need to find out the trace of A plus B. So the thing that we will be going to use here is that sum of the eigenvalues is equals to the trace of the matrix. Okay. And like using this property, I saw like in the last couple of years, at least one question is regularly being asked. So like the sum of the eigenvalue is equals to the trace of the matrix. And the second thing what we know, that trace is linear. That is trace of A plus B is equals to trace of A plus trace of B. Okay. So we see we want to find out this thing, the trace of A plus B. And we know that trace of A plus B is same as trace of A plus trace of B. Okay. And we know what is trace of A. What is trace of A? It is the sum of the eigenvalues of A. And what are the eigenvalues of A? Minus 1, 1, 1, minus 2. And therefore trace of A is what? Minus 1 plus 1 plus 1 minus 2. This is minus 1. Okay. So we know. So for the previous question, can we apply the second method to solve the first problem? That is the row. Yeah, you can solve it. You can solve it, but like this the one that I saw, like the one that I showed you is much easier because then you don't have to see anything. Okay, and there is like because you only have the third, only one vector is in the null, the two vectors in the two, one vector like there are in the, if you go to the first problem, yeah, you see like you have two vectors in the row and one in the null. Okay, so then for the fourth choice you have to choose the first and second both. Okay, so it means that you can write like n of e1 equals to v1, n of e2 equals to v2, n of, let's say this is my v equals to 0, and then for the last thing you have to choose, for example let's choose n of e4 equals to 0. But the thing is that, see, this using this method is much more simpler because just looking at this you are seeing that 1 2 1 4 cannot be in the kernel or it cannot be in the null space, and hence like we don't have to go further. And that is why I told ki even with this method I can solve this problem as well. And this even with this method also, this is not so lengthy. It's like even like when we're doing the exam, it is very easy to compute. Option C, 3, is it correct? Second problem. Uh this, yeah, this is correct, right? This is correct. Okay. So we have computed the trace of A. Now let's see. Yeah. Okay, Avirup. Okay, now I'll see what is the trace of B. So see, what is B? B is A to the 4 minus 5A square plus 5 times identity. Okay. So I have to find out what is trace of B. So the trace of B is what? Trace of B is, as I told, trace is linear. So I can just write trace of A to the power 4 minus trace of 5 times A square plus trace of 5 times I. Okay. Now see, but trace is not multiplicative. It means that trace of AB is not equals to trace of A times trace of B. So this is not true. Okay. Yeah. So, but what we can do, we know this property. I told that this property is very useful, that sum of the eigenvalues is equals to the trace of A. And we know what are the eigenvalues of A. It's minus 1, 1, 1 and minus 2. So, what is the trace of, so if we know that if lambda is an eigenvalue of A, then lambda to the n is an eigenvalue of A to the power n. Okay. And therefore, what are the eigenvalues of A to the power 4? It will be just minus 1 to the power 4, 1 to the power 4, 1 to the power 4, and minus 2 to the power 4. Okay. So, therefore, the eigenvalues of A to the power 4 will be minus 1 to the power 4, 1 to the power 4, 1 to the power 4, and minus 2 to the power 4. And hence, what is the trace? So, trace equals to 1 plus 1 plus 1 plus 16, that's 19. Okay. And similarly, what is the trace of 5 times A square? See, trace, this is 5 is a constant, so I can take it outside. So I'll just take 5 as outside here. Because, okay. And then what is trace? So this is equals to 5 times trace. And what is trace? Trace equals to, so 5 times 1 square. So that is 1 plus 1 plus 1 plus 4. So this is equals to 35. Okay. And there is a minus sign. And then 5 times identity. And what is the trace of the identity function? Is just 1 plus 1 plus 1, that's 4. And 5 times 4 is 20. And therefore, what we got is 19 minus 35 plus 20. And what is this? This is 4. So, we have minus 1 and trace of B is 4. And therefore, minus 1 plus 4 is 3. And hence, the correct answer will be 3. Is it clear to everyone? Because this, as I told, that this property is very important, as well this property is also important. Okay. And you will see that even in today some of the more problems that will be using these two properties. Okay, so let's proceed to the next problem. Yeah, so let A and B be n cross n matrices. And suppose that sum of the elements of any row of A is 2 and the sum of elements in any column of B is 2. Then which of the following matrices is necessarily singular? How to find the eigenvalue of B? See, you cannot find eigenvalue of B directly. Sorry. Yeah, you cannot find the eigenvalues of B directly because if A eigenvalue of A is lambda and eigenvalue of B is mu, then eigenvalue of A plus B is not necessarily lambda plus mu. Okay, so you cannot say what are the eigenvalues of B, because B is the sum of the, like, sum or like difference of the matrices. So you don't know whether the eigenvalues will like how the eigenvalues will behave. The what you can find is the trace, because you know that the trace is linear. So that's why we don't know what are the eigenvalues of B, and you cannot find the eigenvalues of B directly unless until you are given with some other data. Okay, with this data, you cannot find the eigenvalues of B. Okay, yeah. So let A and B be n cross n matrices, and suppose that sum of the elements of any row of A is 2 and the sum of elements of any column of B is 2. Then which of the following matrices is necessarily a singular matrix? Okay. Let's consider one matrix and try to first understand, like, if the row sum is fixed or if the column sum is fixed, then what is the property of that matrix? Okay, so for example, let's take this example 2 0 and 1 1. Okay, so this is a matrix whose row sum is 2. This 2 plus 0 and 1 plus 1. Okay, now If I'll ask you that is 1 comma 1 1, is this is an eigenvalue eigenvector? So let's see what is the uh, what it what is the final computation. So this is like 2 plus 0, that's 2, and this is 1 plus 1, that's like 2 2, which I can write 2 times 1 1. So you see that 2 is an eigenvalue of this problem. And that is in general true that if A is any matrix, let's write A11, A12, dot, 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 A1n, and AN1, AN2, ANN. And if the row sum is fixed, if the row sum is fixed, like it means that sum of the each row is, let's say, lambda, then 1, 1, 1, 1, this is an eigenvector with eigenvalue lambda, where lambda is the sum of elements of each row. Okay, so it means that this sum is lambda, this sum is lambda. Okay, why? Because see, if you are acting on 1 1 1 1, it means that what? You are just adding this, you are adding these all the elements. Okay, so this is like summation a1i, this is summation a2i, and this is summation a-ni. And then I have to remove this lambda. Yeah. Okay. And what is this? I know that everything is lambda. So lambda, lambda. So I just lambda 1 1 1 1. So if the row sum is fixed, then that fixed value is an eigenvalue of the matrix A. Similarly, if the column sum is fixed, see, if the column is fixed, so let's say column of A sum is fixed, then this implies that row of A transpose sum is fixed, because if the column of each column of A sums to a fixed number, then if I'll get transpose, then the column will become the rows, and hence the sum of each row will be fixed, and therefore that sum will be an eigenvalue of A transpose. Okay, so lambda is an eigenvalue of A transpose. Okay. Okay, and we also know that the eigenvalue of A and its transpose are same, and therefore lambda is also an eigenvalue of A. Okay, fine. So therefore, what we have in this problem. So let's see. So I'll just erase it, be it here. Yes. So what we know here, that 2 is an eigenvalue of A, and 2 is also an eigenvalue of B transpose. Okay, so we know 2 is an eigenvalue of A and 2 is an eigenvalue of B transpose. Okay, now I have to find out which of the following matrices is singular. Okay, so the example that I showed you, like the 2 0 1 1, if you will just apply this example, then you will see that this is not singular, this is not singular, this is not singular. So with the example, of course, you can discard these options 1, 2, and 3, and hence 4 will be the answer. Okay. So this is like the elimination method. Like you have one example. This is my A, and you can take B as 1, 2, 0, 1, 1. And if you take A and B, then option 1, 2, and 3 are discarded, and hence the correct option will be 4. But like, but see, these examples may not come to your mind directly in the exam. But this example is the most basic examples that satisfy the hypothesis. But let's see, like, how do you prove that the matrix given in 4 is singular? Okay, so let's see, I minus 1 by 4 BA transpose. So let's see. So I minus BA transpose by 4. Okay, what do you know? That 2 is an eigenvalue of A and B transpose. Here it's B, so let's take the transpose. So if I'll take the transpose of this whole matrix, what I'll be getting? Transpose is again linear. So this is I transpose, that's I minus BA transpose by 4 transpose. But this is what? This is my I minus AB transpose by 4. Okay, fine. Okay. Now what I will do, I'll take V as the vector that I told you, 1, 1, 1, 1. And now what is I minus AB transpose by 4? See here one thing, one caution is there. The eigenvalue of B is 2, B transpose is 2 and A is also 2. So I cannot directly say that the eigenvalue of AB transpose is 2 times 2, 4 and 4 by 4 is 1 and hence I minus this eigenvalue is 0. We cannot directly say. Okay, because as I told, the sum of the eigenvalue will not be the sum of like if lambda is an eigenvalue of A and mu is an eigenvalue of B, then lambda plus mu need not be an eigenvalue of A plus B, and same holds for the product. But what I'll do, I'll just act on this vector. Okay, so what is this? This is IV minus A B transpose by 4 times V. IV is what? It's V minus what is A by 4 and B transpose V. I know that B transpose V is 2V. This is my 2V. So here I can write V minus A by 4 times 2V. And this will get cancelled and therefore V minus A by 2V. And now what I know that AV is equals to 2V. This is also I know. Okay. So therefore A minus V minus 2V by 2. So that's V minus V and hence 0. And therefore 0 is an eigenvalue and therefore this matrix is singular. See, what is the problem if you have the general product? So let's see. Yeah. So if you have a general product, let's say AB and let's say lambda A V1 equals to lambda V1 and B V2 equals to mu V2. So the problem is if you apply in general product, so A, B, V2 if you will take, then the first step is find that you will be getting A mu V2. But now this is mu A V2. And A V2 you don't know because you don't know whether V2 is an eigenvector of A or not. Okay, so you don't know here. But the in the last problem, the best thing was that V, which was 1, 1, 1, 1. So this was eigenvector for both this, like A and B transpose for both. That is why we can do this multiplication trick there. Okay, and this is not in general true because the eigenvector is being changed, and therefore, so be cautious with these things. Okay, and hence what we saw that this is singular. Okay, so the correct option will be 4. So yeah, is this clear? So this property, as I told, this property is useful that the row sum is same, then that is an eigenvalue, and if the column sum is same, then that is an eigenvalue of the transpose matrix. And eigenvector is what? 1, 1, 1, 1. This is the eigenvector. So if you have any problem, you can write or we can proceed. Okay. So I hope you don't have any problems. Okay, so let's proceed to the next problem. Yeah, so M is a given matrix and 1 is an eigenvalue of M, then which of the following statements is true? Minus 2 is an eigenvalue of M, 3 is an eigenvalue of M, and the eigenspace of each eigenvalue has dimension 1 and M is diagonal. Okay, so you can try this problem. And this is a bit like little bit easier than the earlier problem. Yes, so Sachin, so yeah, as I told, if a row sum of A, each row, it means that each row sum of A is lambda, then A sorry, 1 1 1 is equals to lambda 1 1 1. This is always true. So 1 1 1 is always an eigenvector of A. Um, why did we apply V on the transpose matrix? Yeah, because see, yeah, that's a good question. See, the thing is, we don't know if we apply I minus BA transpose by 4V, if we apply on B here, so we don't know whether A transpose V is equals to 2V. Because see, what we know is that 2 is an eigenvalue, but we don't know whether V is an eigenvector of A transpose. We know that V is an eigenvector of A, but we don't know whether V is an eigenvector of V transpose or not. So this we don't know. This we don't know. What we know is like, yeah, there is some vector that will act on A transpose and will give you 2. But we don't know whether that vector is 1 1 1 1 1 or not. And that is why we first take the transpose of that, and then we know that this V is an eigenvector. And transpose is singular, then the matrix is also singular. Is it clear, Manmohan? Okay. So, yeah, I hope it is clear. If not, then let me know. Okay, fine. Yeah. So let's proceed to the next problem. So M is this, and 1 is an eigenvalue of M, then which of the following statement is true? Okay. So what I told, that the one very important property of eigenvalue is that sum of eigenvalue equals to the trace of A, or here it's M. And there is one more important, like we just say the product of eigenvalue is equal to the determinant of n. Okay, so what we know, that sum of eigenvalue is equals to trace and product of eigenvalue is the determinant. So what is the sum of this? 5. The like trace is 5, so trace equals to 5, and therefore if let's say 1 lambda 2 and lambda 3 are the eigenvalues, then what are the two are, like what I can say, that 1 plus lambda 2 plus lambda 3 is equals to 5, and therefore lambda 2 plus lambda 3 is equals to 4. Okay, and now we'll apply the determinant. So if you find out the determinant of this matrix, so what is the determinant? So determinant of M is, I guess, 4. Yeah, it is 4. 4. So, so determinant is equals to 4, which implies 1 times lambda or 2 times lambda 3 is equals to 4, and therefore lambda 2 times lambda 3 is equals to 4. Okay, so you have the sum is 4 and product is 4. So then what is the lambda 2 minus lambda 3 square, or what is lambda 2 and lambda 3? It's basically lambda 2 plus lambda 3 square minus 4 times lambda 3, and this is what? This is 4, so it's a 16, and minus 16, so this is 0. So this implies lambda 2 equals to lambda 3. And therefore, lambda 2 equals to lambda 3 equals to 2. Okay, so what are the eigenvalues of this problem? 1 was already given, and the other two eigenvalues are 2 and 2. And therefore, these two options are false. So now we have to see whether M is diagonalizable or the eigenspace of each eigenvalue has dimension 1. Okay. So see that we know that diagonalizability has one equivalent condition. So let me add a page here. Yeah. So we know that A is diagonalizable if and only if. So there are some, like for example, if and only if all like it has n linearly independent eigenvectors. Okay, so if you have n linearly independent eigenvectors, then A is diagonalizable. Okay, so let's see with 2 how many linearly independent eigenvectors are there. Okay, so we will consider A minus 2i. So what is this? So A was your m minus 2i. So let me just this A, I'm writing it. Yeah. So if you'll just write this m minus 2i, then you'll be getting 2 minus 1 0 1 0 minus 1 1 1 1. Okay. So this is m minus 2i. Okay. What is the rank of this matrix? So see that it contains a 2 block 2 cross 2 sides here. So this determinant is non-zero, and hence the rank of m minus 2i is 2, and therefore nullity is 1. And therefore, how many eigenvectors, linearly eigenvectors you will be getting? Only 1, because nullity is 1. And therefore, the dimension of the eigenspace, the dimension of the eigenspace is equals to 1. And hence, since it is 1 and you have which is not so since there are only two linearly independent vectors, one corresponding to 1 and one corresponding to 2. So one with this and one with 2. So this is false and hence this is correct. Okay. So yeah, if it is clear, then we can proceed, or if you have any problem, then you can ask me. Okay, then let's proceed to the next problem. So let n greater than 1 be fixed natural number, then which of the following is an inner product on the vector space of n cross n real symmetric matrices? So your vector space is n cross n. So A is in M and R such that A is symmetric. That means A equals to A transpose. So this is my vector space. And on this vector space, we have defined four things, and we have to see that which of them is an inner product. Okay. So recall that. I'll just write the inner product thing, that inner product satisfy that x is greater than equals to 0, and this is equals to 0 if and only if x equals to 0. So this is called positive definite, and the one is symmetric since we are in real, otherwise it's a skew, it's a like the transpose symmetric. So usually this is this, but since we are in real, so we don't include this. And then it is linear. So alpha x plus y comma z is equals to alpha x z plus yz. Okay, where alpha is in R. So these are the three properties of the inner product, of an inner product. Okay. So try this problem, and this is very easy. Like if you choose a right matrix A and B to like rule out the various options. Okay. So see, if I'll take A equals to, see, let's see here. What it says that let's talk about these three options. Inner product of AA equals to trace of A times trace of A. Okay. So if it is zero, like, does it imply that A is also zero? C is false. Right, C is false. Yeah, this is right. C is false. But we have to say which of them is an inner product. So this is wrong option. So 3 is wrong option. Please explain the last part of the previous. Okay, I'll explain. Let me finish this and then I will again go to the last part of the previous problem. So what is this? Inner product of A is the trace of A times trace of A, which is 0. So does it imply that A has to be 0? Not necessarily, no? For example, if I'll take, uh, yeah, let's take A equals to 0, 0, 1, 0. If this is the thing, then what is the trace of A? Yeah, right. Right, Khalid, it is not. So trace of A equals to 0, but A is not 0. But A is not 0. Okay, so this does not satisfy the positive definiteness. Same, the same matrix will work for second and third. Okay, because the determinant of A is 0 and but A is non-zero. Similarly, the trace of A plus trace of A is 0 but A is not 0. Okay, so these three are wrong and hence this is true. But you can also show that is not difficult. So let's just quickly see why that's an inner product. So see, the only thing that is like that remains to check is the positive definiteness. That is AA is greater than equals to 0 and equals to 0 if and only if A equals to 0. But what is trace of A times A? Because here we are taking A and A is a symmetric matrix. So what is this? So if I write, see, what is trace of what is A times B? If I write, what is A times B? A times B, if I write ij entry, this is what? A I k times B k j, where k running from 1 to m. So similarly, if I write ij, and I have to compute what is the trace of this matrix. So I just have to compute the diagonal entry. So what is the ai? So this is what? Summation A I k times A ki. Okay, I equals to 1 to m. But A is what? A is a symmetric matrix and hence AKI is same as AIK and then this is what? AIK. So this is nothing but summation AIK square. Now you see that each, what is then trace? Trace is, so if I'll say this is lambda 1 square, then trace is what? Lambda 1 square plus lambda 2 square plus lambda n square. So in like each of the diagonal entry is a square. So trace is what? This plus this plus this plus this. So it's like this line. And each of them is in a square. And therefore this is equals to 0. It means that each of these elements are 0. And therefore each of this will be 0. And hence the matrix A will be 0. And therefore this is an inner product. Okay, and in general, let me just write in general. So this is, so here it was symmetric matrix, but in general, like AB equals to the trace of AB transpose, this is an inner product. So this you can check that this is an inner product. Okay. Yeah. So I hope this is clear. Let's go to the previous problem. Yeah. So he asked why M is diagonalizable is false. So see, as I told, M is diagonalizable if and only if you have n linearly independent eigenvectors. What is the size of M? Size of M is 3. So M is diagonalizable if and only if M has 3 linearly independent eigenvectors. Okay? But now you see, so yeah, I'll just erase this. Okay. So there one eigenvalue was 1. So corresponding to this, we have only one eigenvector. Okay? Because we know that this is algebraic multiplicity and this is geometric multiplicity. And we know that algebraic multiplicity is less than equals to geometric multiplicity. So this is 1, it is 1. Okay. So now lambda 2 is 2. Okay, and and it was 2 2, so algebraic multiplicity was 2. So the geometric multiplicity was 1. Okay, we obtained that the null the m we obtained that m minus 2I, the nullity of this is 1, and hence you have only one linearly independent vector or one non-zero vector which is in the null space, and hence there is only one linearly independent eigenvector corresponding to eigenvalue 2. Okay, and therefore so with 2 gm equals to 1, and hence what is the total gm? It's only 2. So you have only two linearly independent eigenvectors. So one is sorted. So if 3 is not there, so that is why this is not diagonalizable. Okay. So is this clear, JCD mathematics? Okay. So yeah, I hope, yeah, okay, I hope it is clear. We can proceed to the next problem. Yeah. So here V is A is in 3 cross 3 such that A transpose A is in the Ri. So it means that A transpose plus A is equals to some lambda times I. Okay. Okay. And now it says that I is an identity matrix and consider the quadratic form defined as this. So we recall that any quadratic form, if I have X, then it is like X transpose A X. Okay, where A is a symmetric matrix. Yeah, oh right, yeah. I wrote it. Right. Geometric multiplicity is lesser, right? You are right. Yeah. Algebraic multiplicity is greater. Right. Thank you. Yeah, right. Yeah, geometric multiplicity is lower. Yes, right. Thank you. Yeah. Okay. Yes. So, yeah. So this is the quadratic form in general. Now, see, what is the signature of the quadratic form? Because it is asked what is the signature of a quadratic form. So signature of the quadratic form. So what we will do, we'll find out the eigenvalues of A. Okay. So suppose that, so eigenvalue of A is like something like some value is positive, negative, 0. It's like then signature will be positive, negative, 0. Okay. So we'll see that how many positive eigenvector, how many positive eigenvalue, how many negative eigenvalue, and how many zero eigenvalues are there, and that will determine the signature. Okay. So first, let's determine what is the quadratic form. Like what? So if I write what is the so here I have to write this transpose times some matrix here times this. So we have to find first this matrix. So for that, let's simplify trace of a square minus trace of, means trace of a square minus trace of a square. So for that, let's use this, like how A is, like how A looks. So if A equals to, A is 3 by 3, so A11, A12, A13, A21, A22, A23, A31, A32, A33. If A is this, then A transpose plus A is equals to lambda times identity. So it's 1 0 0 0 1 0 0 0 0. Okay. So what is this? If you write, so you'll be getting, see, A11, so it's 2A11, A12 plus A21, and A13 plus A31. Similarly, here we will be getting again A12 plus A21, 2 times A22, A23 plus A32, and this is A13 plus A31, and this is A23 plus A32, and this is 2 times A33. And this is what? Lambda times 1 0 0 0 1 0 0 0 1. Okay. So if you simplify this, so then what is A11? It's lambda by 2. So A11 is lambda by 2, which is same as A22, which is same as A33. And rest of them satisfy that this skew symmetric property. That means Aij plus Aji equals to 0 if I not equals to j. Okay, because see, A12 plus 21, A13 plus 31, these all elements are 0. Okay, these all are 0. So therefore A will look like lambda by 2, A12, A13, minus A12, lambda by 2, A23, minus A13, minus A23, and lambda by 2. So this is my A. Okay, now what I have to find out? So now I have to find out trace of A square plus trace of A whole square. Okay, so it's just like what is A square? If you compute A square is like this, a square. So I'll just write down the trace. So because this is just a computation that you can do the computation. So I'll just write what is trace of A square. So this is equals to 3 lambda square by 4 plus, sorry, minus 2 times A12 square plus A13 square plus A23 square. And this is this, and trace of A square. What is trace of A? It's 3 lambda by 2, so it's plus 9 lambda square by, oh, so this was, let's not do this, yeah. Yes, this is 9 lambda square by 4. Okay. Now what is Q of A? Q of A is given trace of A, where I have written, yeah, trace of A square minus, right, trace of A square minus trace of A square. So just write down this. So this is 9 lambda square by 4 minus 3 lambda square by 4 plus 2 A12 square plus A13 square plus A23 square. And what is this? This is 6 lambda square by 4 plus 2 times A12 square plus 2 times A13 square plus 2 times A23 square. Okay. So this is my the quadratic form. Okay. So it means that this so this means, what was the dimension of V? Dimension of V was 4. Okay, because see, there are only 4 arbitrary constant. One is lambda, A12, A13, A23. Okay, so it means that Q. So instead of A, I can just write lambda, A12, A13, A123. So this is what? This is this quantity. So this is my quadratic form. Okay, and now this will be something transpose, as I told, some matrix times, so X transpose times X, and this matrix we need to find out. Okay, okay, but you see, in the quadratic form, you only have the quadratic terms. You only have the quadratic terms. So you don't have the mixed term. See, in general, how the quadratic look like. Like if you write like quadratic of let's say xy. So how it will look like? It's look like ax square plus bxy plus cy square. So this is like the mixed term. So the matrix of this will be what? A, b by 2, b by 2, and c. Okay, so in the diagonal, we write the square term. So if I write this, so it's like what? So 6 by 4 is 3 by 2. So 3 by 2, 2, 2, 2, and rest of them is 0. So this is the matrix of this quadratic form. This is the matrix. Okay, and hence, what are the eigenvalues of this? 3 by 2, 2, 2, and 2. So 4 eigenvalues are there. 3 by 2, 2, 2, and 2. And all of them are positive. And therefore, what is the signature? Signature will be plus 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 plus. Okay. Okay, is it clear to everyone? Yeah. Do you have any question? Yeah, this completes the part B. So if you have any problem from from the part like problem 1 to problem C, then you can ask now, and then we will go to the part B, I guess now. Yeah, part C. Yeah. So I hope it is clear. So just to summarize here some of the properties. So I'll just summarize some of the properties that we, so the first thing is the sum of eigenvalues equals to the trace product of eigenvalues equals to determinant. Third thing, that if a row sum is same and say lambda, then lambda is an eigenvalue of A with eigenvector 1, 1, 1. Okay, and right, and fourth thing is the quadratic form. If Q of V equals to V transpose AV, then the sign of eigenvalues of A determines the signature of Q. Yeah, so right. So I wrote 6 by, but what is 6 by 4? 6 by 4 is 3 by 2. That's why I wrote 3 by 2. You can write 6 by 4, no problem. We just need to see whether it's positive or negative. So 6 by 4 is basically 3 by 2, so that's why I wrote it. Okay? Okay. So, right. Yeah, so sum of eigenvalue is the trace of the matrix, product of the eigenvalue is the determinant, and if row sum is same, then that value is an eigenvalue with eigenvector 1, 1, 1. And if you have a quadratic form V transpose AV, then the sign of eigenvalues of A determines the signature of that quadratic form. And fifth is if lambda is an eigenvalue of A, then lambda to the n is an eigenvalue of a to the n. Okay, so these are the properties that we have used till now. Okay, so we can proceed to the next section. I hope you don't have any further problems or questions. Okay, yeah, right. So let A be an M cross N matrix such that the first R rows of A are linearly independent and the first S columns of A are linearly independent. So let's draw a rectangle which is M cross N. So this is my M cross N, and it says that the first R rows are linearly independent. So let's say this is my first R rows and this is my first S columns. Okay, so this is R and this is S. Okay, so these are linearly independent and these are linearly independent. Of course, I don't know about this and this. I know that these rows are linearly independent and these columns are linearly independent. Then which of the following statements are true? The first statement, the rank of A is at least max of RS. Does order matter in signature? No, it's like usually we write like uh, if it is like three pluses are there, then we just write 3, 0, minus 3. Sometimes we write that also. So, so the order won't matter in the signature. Okay. So the rank of A is at least max of RS. This is the first option. So what is the guess? Do you have any guess of this problem? Whether the option A is true or false? If you have any guess, you can write about the option 1, that the rank of A is at least max of RS. So it is true, right? So it is true. So why it is true? So see that what is the rank of a matrix? The rank of a matrix is it's same as row rank and that is same as column rank. Okay. So what is the row rank here? Row rank is at least S. Okay. Sorry, row rank is at least R and column rank is at least S. And we know that the rank of a matrix is equals to the row rank and equals to the column rank. So rank of a matrix A is equals to row rank of A, which is equals to the column rank of A. But this quantity is bigger than equals to R and this quantity is bigger than equals to S. So therefore rank of A will at least be the maximum of R and S, and therefore this option is true. Okay. What about the second option? The submatrix formed by, so this matrix is asking, what is the rank of this? Whether the rank is equals to minimum of R and S. I didn't understand this step. I minus A by 4. Okay, Aarti, I'll just explain after I'll finish this problem, the seventh problem, then I will go back to that. Yeah, Surya Narayan. Yeah, false. Right. So can you give me an example? That's right that this is false. So let's see. Yeah, you are right that this is false. So rank of this, rank of this matrix need not be equals to the minimum of R and S. Yeah, if it is written less than equals to, then true. Right, you are right. So for example, see, if I'll just take 1, 0, 0, 0, 0 and 0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, not 0, let's take here, I'll just take 1, yeah, otherwise it won't be, yeah, yes. I'll take 1 here and then 1 here. And then you can take anything 0, 1, or anything. Yeah, just take 4 by 4. Sufficient. Okay, right. And yes, yeah, let's take this matrix. And if I take R equals to, let's say, 2, so R equals to 2 means this. And these two are linearly independent. That's true. And if I take S to be, let's take this 2. Okay. So, right. So R is 2 and S is 2. So, and what is the, so this matrix, and what is the rank of this matrix? Is equals to 1. Okay. Which is less than minimum of R. So it may not be equals to, because as I see, you have many zeros to fill out here. So you can fill many zeros. So that's why this rank has to be less than equals to the minimum. So this option is false. So this is less than equals to minimum RS. Okay, right. So let's see the third option. If R is less than S, then there exists a row among the R plus 1 to M, which together with the first R rows forms a linearly independent set. What do you think? Is it correct, or is it is false? So now R is less than S. And what do you know? That the rank of matrix is true, right? Because the rank of the matrix is maximum of R and S. So it means that the rank of the matrix now, rank of A is bigger than R, because R is less than S. Rank of A is bigger than R. Okay, it means that what? Rank of bigger A is bigger than R. It means that you at least one linearly independent vector will be there, and hence this is correct. What about the fourth option? If S is less than R, then there is a column among columns this, which together with the first S column forms a linearly dependent. This time it is dependent. See, if it would have independent, then this option is of course true as same. But what about dependent? Is it true? Any idea about the option 4? No, it is not true, right? So you see that this example itself will work. Like here, you see S is less than R, so this example won't work, right? Because see, you have the linearly dependent set. So you have the if R equals to S plus 1, right? So it's like you see, you know about the linearly independent set, that there must be some linearly independent, but we don't know whether some linearly dependent set will be there. Yeah, right. So this option is false. Yeah. So, right. So therefore, what are the correct options? 1 and 3. Okay, right? It is clear. Okay, so now let's go to the Arti's question, which she asked like she did not understand the steps in I minus. Okay, so let me add the page here. Okay, so see, uh, let's. So I'm claiming, let me write it formally now. I'm claiming that 0 is an eigenvector, eigenvalue of I minus A. It was A beta transpose, yeah, A B transpose by 4. Okay. So is it clear that if 0 is an eigenvalue of this, then this implies that I minus A B transpose by 4 is singular. Okay. So if 0 is an eigenvalue of this, then this is singular. Is this clear, Arti? Is this thing that if 0 is an eigenvalue of this, then this is singular? Okay. So what I will show that 0 is an eigenvalue of this. Okay. So what I know, if V equals to 1, 1, 1, if this is V, then what I know that AV equals to 2V because the row sum was 2 and B transpose V equals to 2V because the column sum was 2. Okay, so I'll just apply this. So I'll I minus AB transpose by 4. I'll take V. So what is this? This is IV minus AB transpose by 4V. But what is this? IV is an identity matrix. So IV is V minus A by 4 times B transpose V. Okay. And what is B transpose V? B transpose is 2V. A by 4 times 2V. So that is B minus A by 2V. Sorry, A by 2V. Okay. Now what is AV? AV is 2V. So this is equals to V minus 2V by 2, which is equals to V minus V, which is equals to 0. So this 0, so what I showed that this equals to 0. So this means this equals to 0 times V. I can write 0 as 0 times V, and hence this is an eigenvalue. And therefore 0 is an eigenvalue of this matrix. And hence this matrix is singular. And that is what in the option it was asked. Is it clear, Aarti? Okay. So then we can proceed to the next problem. Right. Option will be reduced to S minus R linear. Right, Manmohan. Yes, you are right that since R is since the rank of A is bigger than equals to S, so therefore R is here, S is here. So of course S minus R more linearly independent. So S minus R more linearly independent elements will be there, right? Yeah. Yeah, thanks for the observation. Yeah, right. Okay. Let's go to the next problem. Yeah, this is the next problem. So if A is an M cross M matrix with real entries and let X be a M cross 1 vector of unknowns, and now consider the two statements given below. So now A is in a square matrix, and so the first option is that there exists a non-zero vector B1 in Rm such that the linear system Ax equals to B1 has no solution. And the second option is that there exist non-zero vectors B2, B3 in Rm with B2 not equals to CB3 for any C in R such that the linear system Ax equals to B2 and Ax equals to B3 have solutions. Again, we have to see which of them is true. So 2 is true whenever A is singular, 1 is true whenever A is singular, and 1 and 2 can be true simultaneously, and if M equals to 2, then at least one of the 1 and 2 is false. Okay. Right. So, do you have any guess about the considering, let's say, this statement, the first statement? So, first is this. Okay. So, what about there exists a non-zero vector? What do you think? That given any matrix, or here it's singular, of course, here it's a singular matrix. So, if A is singular, can you find a non-zero vector B1 such that Ax equals to B1 has a solution? So you are saying this is false. So Surja is saying this is false. So I'm talking about the second option, Surja, not the first option. So yeah, so let's see whether it's true or false. See what it says that A x equals to B has a has no solution. Okay, I have to find a vector B1. Okay, let's see. So this is my A and this is my B. So this is my augmented matrix. So what do you know? When do we have a solution of this matrix? When do we have a solution of Ax equals to B? If rank of A equals to rank of the augmented matrix. If we have this, then only we have a solution for this equation that ax equals to b. So here the problem is, like, given A, can I find a B such that this has no solution? And note that A is singular. So A is singular means what? The rank of A is less than n. So at least after, like, or after the after doing the, like, this pivoting and all, I'll be getting at least 1 0 row here. So if I choose my B as, let's say, here as 1, and you can take anything B here. So does this have a solution? Yes, right. There exists. So for every B, it is not possible. Right. So it's just say, does there exist a non-zero vector? Right. So this statement is true. Okay, because it says that does there exist a non-zero vector? It does not say that for every B. Okay, so this is fine. Now let's see the option, the second statement, and option one. Yeah, what do you think? So 2 is true whenever A is singular. Yeah, so any guess? So 2 is true whenever A is singular. So it means that if I give you A a singular matrix, can we find out B2 and B3 linearly independent vectors such that AX equals to B2 has a solution and AX equals to B3 has also a solution? Is it always possible? See, now A is singular. Okay. So what I know, that at least one of the row will be 0. Okay. So what if you take the size of A to be 2? So for example, let's say if I'll give you A as 2 cross 2 matrix. So A is, let's say, 1 0 0 0. Let's say this is my A. And if I'll now see, of course, you can choose B1 as, let's say, because this is 0, so this you have to take 0, and this, let's say, something, anything like B is, let's say, 1. So A is this, and this is my B1, B2. Then of course this has a solution. So AX equals to B2 has a solution. Fine. But now can you for this A, can you find a B3 which is linearly independent to B2 and has a solution? So if it is linearly independent to B2, it means that it has a form like this. Okay? Now if it has a form like this, then A, rank of A is what? 2, but rank of augmented is, rank of A is 1 and augmented matrix rank is 2, and hence this does not have a solution. And therefore, this is not true if M equals to 2. So if you take the dimension of the matrix to be 2 and rank of the matrix to be, like, A to be 2 cross 2 matrix, and the rank of the matrix is 2, then this need not be true. Of course, if it is higher, like if A is at least 3 cross 3, then this is always true. Then this is always true. But if A is 2 cross 2, then this need not be true. And hence this option is false. Now both 1 and 2 can be true simultaneously. Of course it can be. For example, I take, if A, as I told, if A is 3 cross 3 or higher, then 1 and 2 is always true if A is singular. Okay? So this is true. What about fourth option? If M is true, then at least one of 1 or 2 is false. So yeah, any guess about the option 4? Yeah, so option 4. Any guess? Okay, so okay, let's see. So M equals to 2. So A is equals to 2 cross 2 matrix A, B, C, D. Okay. So see. what are the possibilities of A? So rank of A could be 0, or it could be 1, or it could be 2. Okay, so there are only three cases can be happen. Rank of A is 0, rank equals to 1, and rank equals to 2. Okay, so R means rank. R means rank. Okay. So see, if rank of A is 0, it means that what? A is a 0 matrix. Okay. But if this is, then can, like, then of course, then 1 is of false always. Because AX equal, oh sorry, 2 is always false. Okay. So if this is, then 2 is false. Because as we saw in the even in this, when we were seeing this, we saw that if it is option 4 is false, right? Option 4 is false. Yes, option 4 is false, you are saying. Let's see it is false or not. So as I told, rank of A could be either 0, 1, or 2. So if it is 0, then 2 is false, and hence one of them is false. Fine. What about rank of A is 1? If rank of A is 1, then it will be something like AB 0, 0. Then again 2 is false. Okay. So, and what about rank 2? If it is rank 2, then AX equals to B1 has always a solution, and therefore option 1 is false. So in any case, if M equals to 2, then at least 1 or 2 is false. Okay. So this option is true. So did you understand, Manmohan? So we consider the rank to be either 0, 1, or 2. So if rank is 0, then the second is false. And if rank is 1, then again second is false. And if rank is 2, then 1 is false. So in any three conditions, one of them is false. Okay. So is it clear to everyone? Then we can proceed to the next problem. This. That if M is an n cross n matrix such that M is not 0, but M square is 0, then which of the following are true? Okay. So do you can try this. Okay. So I'll just give you a hint. So what is the here? Can you say something about image of M and column of M? Is there any relation between image, image and null, kernel of M? Do you see there is any relation between image of M and the kernel of M? So if yes, then what is a relation between image and the kernel here? So see, if I take a W in the image of M, so what does this mean? This means that there exists some V such that MV equals to W. This is the meaning of that image, W is in image. Okay. So MV is equals to W. So this implies M of MV is what? Equals to MW. But what is this? This implies M square V equals to MW. But M square is 0. And therefore this is 0. And therefore MV is 0. And hence V is in the kernel. So you see, we started with a W in image. Sorry. Right. Just a minute. W. Sorry, I've written. My bad. Sorry. Yeah, that's MW. So this implies MW equals to 0, and therefore W is in the kernel. Okay. So W is in the kernel. So this implies this is true. So image is contained in the kernel. Okay, so if now we know that this all are vector space. So if this is contained, then what can you say? If V is contained in W, then dimension of image of M is less than equals to dimension of kernel of M. Okay, and therefore, and now you see what is the dimension of image of M? That is same as the dimension of column of M, because this is equals to rank of M, and this is equals to nullity of M. Okay, but rank is same as the column rank, and therefore this is same as dimension of column of M, and this is equals to dimension of null of M. And this, so we have dimension of column is less than equals to dimension of null, and therefore this is false and this is false. So these two options may be true, and this is the third is always true. Let's see about the fourth, where the equality can hold or not, if n is even. So see, if n is even, then let's see the equality can happen. So if dimension of column plus dimension of null is equals to rank, okay, and rank is what? Equals to n. And n is even, and these two are same. So these two are same means 2 times dimension of null or dimension of this equals to n. And this is even, so this equation is right. And therefore, this is also right. So equality can occur if n is even, then equality can also occur. So these two options are true. Okay, so this was an easy problem. Just we have to observe this property that image is contained in the kernel. Okay, let's proceed to the next problem. Yeah, this problem is about the diagonalizability. So let A be an n cross n matrix, and we say that A is diagonalizable if there exists a non-singular matrix P such that P inverse is diagonal matrix. Okay, so this is just a definition that A is diagonalizable if you can write A as it is non P inverse such that this is equal to some diagonal matrix. Okay, if this is equals to some diagonal matrix, then we say that A is diagonalizable. Okay, and now we have to see which of them implies that A is diagonalizable. So recall that A is diagonalizable if and only if. So there are certain things. So first thing is it has n linearly independent eigenvectors. Okay, or if the minimal polynomial is linear. Linear means it's like linear in each. So there is no power. So I should write each like x minus a times x minus b times x minus c, this kind of thing. Then A is diagonalizable. Okay. So let's see the first option. What is the first option? That there exists an integer k such that a to the power k is I. So you have given that a to the power k equals to I. So this means what? X to the power k minus 1 equals to 0. Now we know that minimal polynomial will must satisfy this. Okay, so minimal. So what are the roots of the minimal polynomial? The roots of the minimal polynomial will be the roots of this polynomial. And what are the roots of this polynomial? These are the kth root of unity. So it's like all the numbers on the kth root of unity. So all are distinct. So all roots are distinct. And this implies minimal polynomial. So all the roots of the minimal polynomial are distinct, and hence this is A is diagonalizable. Okay, So therefore this option is true. Okay. The second option is, of course, fourth option is true. A has linearly. No, so fourth option has A has linearly independent eigenvector. So I don't know the like what like so. See here it is not written A has n linearly independent eigenvectors, because of course if A has five, if A has n minus one linearly independent eigenvectors, then it may not be diagonalizable. So these options, this the option 4 may not be true. So I don't know the actual answer key. So, but according to me, this is false because the n is not mentioned there. Here. N is not mentioned. Yeah. If in the answer key, if it is marked as right, then it means that they are assuming it is n linearly independent. But apparently, this is not clear. Yeah. Let's see what about the second and third. So there exists an integer k such that a to the power k is nilpotent. So see, if I take a as 0, 1, 0, 0. So then a is nilpotent. A is nilpotent. Okay. So a is nilpotent. So but is A is diagonalizable? No, A is not diagonalizable. This is not diagonalizable matrix. In question, it is not mentioned diagonalizability or ROC. So video agent. Yeah. So right. So yeah. So here, if it is not mentioned, so we'll take field to be C. Of course. Otherwise, we cannot say the roots of this equation. Right. So whenever it is not mentioned, like about which field we'll be talking, then we always take field to be C. Of course, this is also a loophole of this problem. But yeah, if it is not mentioned, we take field as C. Right. Okay, so right. So then this is, so what it says that there exists an integer k such that a to the power k is nilpotent. Does this imply that a is diagonalizable? So here A is nilpotent, so it means that k equals to 1. So A is nilpotent, so there exists k such that a to the power k is nilpotent. But A is not diagonalizable, and hence this option is false. And this option is false. Sorry, not this, the earlier one. Now, what about A square is diagonalizable? Does this imply that A is diagonalizable? No. The same, the same example. You see this A. What is A square? A square is 0, 0, 0, 0. No, what is A square? Sorry, 0, 1, 0, 0. Yeah, it's 0, 0, 0, 0. Yes. So this is diagonalizable. A square is diagonalizable, but A is not diagonalizable. Okay, so this is also false. This is also false. So this is the correct answer. Okay, so let's go to the next problem. So if you have any question, you can ask now. I'll give a pause for 4 to 5 minutes. And if you have any question, you can ask. Any previous problem here, if you have any doubt, you can ask. Okay. So if no, then let's proceed. So this problem that, yeah, it is none that x equals to x0 is in M2Z. If field is R, then whether option 1 is true. No, then you cannot, then option 1, because it's diagonalizable over C, but it need not be diagonalizable over R, because we don't know, because see, uh, in R, we don't know what are all the roots of the, because how do you write these things? So whenever, that's why in general, when we talk about the diagonalizability and all, here it's in the complete field. or you might say. But yeah, of course, if it is R, then yes, this is not true. The option 1 is not true because you cannot split it. So yeah, okay. Okay, is it clear? So we proceed to the next problem. Okay. So the next problem is in the first problem, please explain about the condition for being the linear transformation. Always just saying that not equal to 0 conclude it is a linear transformation. Just let me see the problem one. Okay, so see, yeah, see. So the thing is, see, what is this? That option one is fine. Option one is false. So let's see the option two. I guess you are asking about the option two. So see, it is given that M is in M4R, and you have like the basis of the column is given. It's like V1, V2. Okay, and the null, there are two vectors V3, V4 given. Yeah, V3, V4 is given. So what I am saying, see, that I need to find a linear transformation M from R4 to R4 such that what? So I need to find a linear transformation from R4 to R4 such that it sends V3 to 0, V4 to 0, and the column, I see the column of M has dimension 2. So it means that the rank of M is 2. So it means that the image will contain V1, V2. So there exists some E1 is V1 and E2 is V2. So does there exist such matrix? Does there exist such linear transformation which sends V3 to 0, V4 to 0, E1 to V1, E2 to V2? So see, of course, so it means that what you need to solve. See, if M is this, and if I write M of V3 is equals to 0, M of V4 equals to 0, M of E1 equals to V1, and M of E2 equals to V2. Can you write down the, if you write down the matrix of M, if we write the matrix of M, and if it is, so if it has rank 4, rank means it not rank 4, so I'll just say, yeah. So let me just compute it better because, yeah, let's just compute it finally since you have doubt. So let me compute it. So M of E1 equals to what is V1? Let me see. V1 is 1110. So it's 1110. M of E2 equals to 1011. 1011, and M of your V3 is 0 and M of V4 is 0. Fine. So I have to write down the matrix of M. Can you write down the matrix of M? Avrikol, what? Avirup? From this, can you write down the matrix of M with the given basis? Because we know that E1, E2, V3, V4, these are the bases we know. So can you write down the matrix of M? How the matrix will look like, because we know that, as I shown earlier, that this is linearly independent and hence this will form a basis of M. So if I write down the matrix of M, so let's write down the matrix of M. So M of E1 is this. So the first will be 1 1 1 0. The second will be 1 0 1 1. Okay. And what about the V3 and V4? Abhirup, are you there? So then, if you can respond, then uh, I don't know whether Abhirup, if you can write down something, because I don't know whether you are there or not. Okay, so okay. I hope you are there, so because I don't know whether you are there or not. Yes, sir. Okay, fine. So see, the thing is that the best way to solve this problem is to write A as or M as or A as 1 1 1 1 0 1 0 1 1 and alpha plus beta alpha plus beta beta al beta and a plus b a a plus b and b. Okay, a is this matrix. Best way to solve is this, like find out the value of alpha beta, and that's not difficult as I showed you here. Okay, now the second way that I told, that since m of v1 is 0 and m of v2 is equal to 0 and m of e1 is v3 and m of e2 is v4, and since we know that I just changed the notation, sorry, right, sorry, yes, this is v3, this is v4, this is v1 v2. Since I know that v3 v4 e1 e2 are linearly independent, and therefore we can find such a linear transformation. Okay, here main thing is that this v3 v4 e1 e2 are linearly independent. But if you have any problem, that's why I told this method, because this method is like, you don't have to be confused anything. It's like you just write down the matrix A as this, and solve for alpha, beta, AB. And this is like very easy to solve. It's like no need to do any much calculation. Okay. So is this okay, Avirup? Okay. So yeah, right. So then we can go to the next problem. So it is known that x equals to this. Okay, fine. It is known that x equals to okay. Thank you. So here ax minus xa equals to a, and where a, for some a belongs to this, and what we have to find out, what are the not possible values for determinant. Okay, so we have to find out the determinant and which of the values are not possible, that we have to find. Okay, so ax minus xa equals to a. Okay, so what can I say from here? So trace of ax minus xa is equals to trace of a. But what is this? This is trace of ax minus trace of xa. But this is 0 because trace of ax is same as, right, first matrix is the only choice for a. Of course, yes. Right, trace of A is 0, right? So trace of A is 0. So it means that this. So it means that A will be this. Yes, you are right. So A will be what? A will be my, since trace of A, so from this condition, trace of A equals to 0. So therefore A equals to 1, 1, minus 1, minus 1. Okay, now we have A. So you just take X as A, B, C, D, and if you do AX minus XA equals to A, then the equations that you will be getting, I'll just write down the equations, they are not difficult. Yeah, so the equations that you'll be getting is like B plus C, 2B minus A plus D, d minus 2c minus a and minus b minus c. And this is equals to a. A is what? 1, 1, minus 1, minus 1. Okay. Then from this, what is b plus c? B plus c is equals to 1. So this implies c equals to 1 minus b. Fine. And let's consider this. So this is what? 2b minus a plus d equals to 1. So from here d equals to 1 minus 2b plus a. Okay. And of course, if you consider this, this is same as this. Because minus b minus c is equals to minus 1, that's same as b plus c is 1. And if you consider this, that is same as this. Let's see why. Because d minus 2c minus a equals to minus 1. If c is 1 minus b, so d minus 2 times 1 minus b minus a is equals to minus 1. This implies d equals to 1 minus 1 and minus 2 will be plus 2 and then minus 2b plus a. So that's same as this. Okay. So it means that you have two conditions. C is equals to a 1 minus b and d equals to 1 minus 2b plus a. So therefore x equals to, I'll just write x equals to a, b, and c is equals to 1 minus b and d equals to 1 minus 2b plus a. Okay, right. So this is my x. Now what is the determinant of x? Let's see. So I'll just add a page. Yeah. So what is the determinant of a? So determinant of a x, sorry, not a. So determinant of x is what? A times 1 minus 2b plus a minus b times 1 minus b. This is the determinant. So what is this? This is a minus 2ab plus a square minus b plus b square. But what is this? This is a square plus b square minus 2ab, which I can write a minus b whole square plus a minus b. And this is what? A minus b I can take common. So this is a minus b plus 1. Okay. So if a minus b, if I'll write just some alpha, then this is alpha times alpha plus 1. Okay. So this is the thing. Now what are the options? So options were 0, 2, 6, 10. So can it be 0? Yes, it can be 0 if I'll take alpha to be 0. Means a equals to b. So let's so it means that if I'll take a equals to b, then this is right. Okay. Can it be 2? Yes, if I'll take a equals to 3 or a equals to 2 and b equals to 1. Okay. Because 2 minus 1 is 1 and then here it's 2. This is also possible. Can it be 6? Yes, this can be 6. Which is not possible? 10 is not possible, right? 10 is not possible. So 6 is also possible. And 10 is not possible because alpha square plus alpha is equal to 10. This does not have an integral solution. This does not have solution in Z. Okay. And therefore, this 10 is the correct option. So this is the correct answer because it is not possible. So this is the thing. Okay. Right. So let's proceed to the next problem. Yeah. Yes, this is kind of an important. So it says that which of the following are inner products on R2? So see, let me write down here. If you have any any inner product on Rn, so let's say x and y, so this is equals to x transpose a y, where a is some symmetric positive definite matrix. Okay, so it means that any inner product you can write in this form. Okay, so let's write that and check whether the matrix is symmetric or not. So this, what is this? If I write the matrix, this is what? 1, 2, 2, 1. Yes, symmetric bilinear with positive definite. Yes, right. Yeah, bilinear will of course be there because it is linear in both the thing. And this is 1, 1, 1, 2, and this is 1, 1, 1, 1, and finally this is 1 minus half 1. Okay. So what I have to check that each of the matrix, it first of all the easy thing to check is symmetry. Of course, everything is symmetric. This is symmetric, 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 symmetric. Now let's take whether it is positive definite or not. So positive definite means each of the eigenvalue is bigger than 0. So positive definite if and only if eigenvalue is bigger than 0. Okay. But see, this is 2 cross 2 matrix. And so we can just, instead of the eigenvalues, we can just see the trace and determinant to conclude it. So for example, for the first example, 1, 2, 2, 1. What is the lambda 1 plus lambda 2? It is 2. Yeah, row sum is 3 in the first. Yes. Yes, so 3 is an eigenvalue. 3 is an eigenvalue, right? Right, you are right. And but data, so 3 is an eigenvalue and the trace is 2. So therefore minus 1 is another eigenvalue. And therefore this is negative, hence this option is false. We don't we don't have to like it's just like since we are in 2 cross 2 matrix, so it's like just check even you don't have to check all the eigenvalues. It's like just check the trace and the determinant will help you to finding out that. Another is negative, so not positive, right? Right. The second option is 1, 1, 1, 2. What, see, first of all, see what is the determinant. Because if determinant is negative, then of course this is not positive definite. Because determinant is what? Lambda 1 times lambda 2. If it is negative, it means that one of them of course be negative. Eigenvalue of C are 2 and 0. Yeah, of course, because 0 is fine. Yeah. So 0 is there. So 0 is an eigenvalue. So this is wrong. And in the second C, 1, 1, 1, 2. So 1, 1. What is the determinant? So determinant is equals to 1, positive, and trace equals to 3. So this is also positive. So now lambda 1 plus lambda 2 is equals to 3 and lambda 1 times lambda 2 equals to 1. So this means that both lambda and lambda 2 are positive. Okay. So this means this is also right. Similarly, if you consider the fourth one, what is the trace? So lambda 1 plus lambda 2 is equals to 2 and determinant lambda 1 times lambda 2 is 1 minus 1 by 4. So that's 3 by 4. That's also positive and this is also positive. So it means that sum of two things is positive and their product is positive. It means that lambda 1 and lambda 2 both are positive and hence this option is also correct. So since it was 2 cross 2 matrices, so that why the computations was a bit easier. Okay, we don't have to compute the eigenvalues here also. Okay, we just have to see the trace and determinant. Okay, so this is the last problem of February 2022. Okay, so what is the problem? So consider the system this in three unknowns x, y, z and one parameter k. And for which of the following values of k, uh, the system of linear equation consistent. So as I told, like if you have ax equals to b, then the system is consistent if and only if rank of A equals to rank of augmented matrix. Okay, and otherwise not inconsistent. Okay, so what we have to see, for which value rank of A equals to rank of A by B. So let's write the matrix. So write down the matrix. So matrix is what? 2 k 0 k 2 0 0 k k. Okay. See, if the determinant of this is non-zero, then it is always, because then we know that the rank is always 3 and hence it is always true. Okay. So let's see what is the determinant of this matrix. So what is the determinant? So determinant is 2 times 2k minus k times k square. So that is 4k minus k cube, and that means I can take k as common. So 4 minus k square. Okay. So see that at 1 and minus 1, this is non-zero. So this means these two are of course true. That since determinant is non-zero, hence this is consistent because the rank will be 3 and hence the rank of A will be 3 and rank of A augmented B will also be 3. We only have to see for 2 and minus 2. So let's put A equals to 2 there. So if I'll put K equals to 2, what is the matrix? So the matrix will be 2, 2, 0, 2, 2, 0, 0, 2, 2, and this is 2 minus 2 is 0, 2, 2 minus 1 is 1. Okay. See, this is like these two are linearly dependent. So rank of this is what? Rank of A, rank of A is what? 2. Okay. And rank of AB is 3. Why it is 3? So you can see this. Okay, you can see that this 3 cross 3 is like linearly independent. Okay, and hence rank of this is 3 and this is 2. And therefore, this option is false. Similarly, if you take minus 2, then what is this? 2 minus 2, 0, 2 minus 2, 0, minus 2, minus 2, 2, 0, and last is 0, minus 2, and here is 2 minus 2 is 4, minus 2, minus 3. Again, you see that these two are linearly dependent. So inconsistent, right? So this is also inconsistent because rank of this is 2 and rank of this whole is 3. So this is inconsistent. So this is also false. So therefore, the correct options is 1 and 3. Okay. Is it clear? Okay. So before going to the some of the problems in June, I'll just uh, write down some of the things or a summary kind of things that, again, because these are the very useful properties. So the first property, I'm writing it again and again, that sum of, because you see that this property we have used several times. Eigen values is equals to the trace of the matrix, sorry, product of the eigenvalues equals to the determinant of the matrix. Third is what? Any inner product. So any, because you will see that this inner product problem will also be appearing in the consecutive years. So any inner product in Rn can be written as, so xy inner product equals to x transpose A y for a unique. So it means that if you have one inner product, then that's the matrix is unique. Unique, symmetric, positive definite, bilinear, and this is a matrix, so it is that matrix A. Okay, so you have symmetric, positive definite matrix A. Okay, the fourth thing, if row sum is same, then uh, the value of the sum is an eigenvalue with eigenvector 1 1 1, like this. Okay, and same as for column. So if for column sum A transpose times 1 1 1 is equals to sum. So if the column sum is lambda, if let's say this column sum is lambda, then this is lambda times 1 1 1 1 1. Okay, and these two are very important property. I'm saying it because like when I was solving some of the last year problems, I find at least like this property was being used in 3 consecutive years. For example, this even in the next like the June 2020 also this property will be used. And let's recall, yeah, the quadratic form is also very important because each year you have at least one problem for the quadratic form. So quadratic form. So Q of x is equals to x transpose A x. Okay, and where A is the is us sorry A is just symmetric. Okay, okay. So this is the thing uh, that we have. I have already listed here some of the properties before, I guess. Uh, yeah, this. Here also I have listed some of the properties. I will do what I will do. I'll just summarize these properties, typed it up, and will share all of you. So I guess all of you who are here is on the WhatsApp group. So I'll share on the WhatsApp group the typing thing. So I'll just summarize everything what we have done till now. I will summarize all the important results, typed it up, and will share with you all the WhatsApp in the WhatsApp group. So if any of you are not in the WhatsApp group, I have given in the description. You can just join the WhatsApp group. Okay, or I'll mail also. It's not a problem. Yeah. Okay. Let's proceed to some more problems. June 2020. Yeah. Manmohan asked, what is a bilinear matrix? So, no, sorry. So, there is no right. Right. Sorry. A is not a bilinear. Sorry. So, A is a linear matrix. Sorry. That is my mistake. So, A is linear. No? A is a matrix, so hence it's a linear. Bilinear means you have two things, like bilinear means f from v cross v to some, let's say v or r or anything. So it's like you have two inputs, but yeah, so A is linear. So yeah, so I'll just make it here, right? Yeah, I'll just write. A is just symmetric positive definite, yeah. Right. The inner product is of course bilinear. Yeah, inner products are bilinear algebra, right? Like, for example, x comma y, and this is bilinear, of course, in when it is uh, real, but it is not bilinear on the complex. For example, in the complex, this is not bilinear. So, like for example, like alpha x comma y, this is of course alpha x y. This is of course true, but x alpha y, this is not equals to alpha xy. So this is not true. So in complex, the inner product is not binding. So in general, the inner product is only, it's like so that's why the inner product is only positive definite, symmetric, and linear in the linear in the first variable. First variable. And of course, if it is symmetric when you are taking, so then it is linear in the both variable. Because otherwise it's conjugate symmetry. Okay, and then This is not in the second, it is not. Okay. So, but yeah, of course, if you are a R, then it is bilinear. Okay. But this property is very important that given an inner product, you can find a matrix A symmetric positive definite such that you can write this inner product as this. Okay, this is a one-to-one correspondence. Means like if you give me an inner product, I'll give you a matrix A, and if you give me a matrix, I'll give you a inner product. Okay, and how to determine this matrix A? How to determine this? So in general, xy equals to, let me write down since this is an important property, this times y, where this is E1 E1, where E1 E is the standard basis, and the ijth will be Ei Ej. Okay, so this is the matrix. Okay, okay. So yeah. Thanks for clearing out. Okay. So now we'll talk about some problems from June 2020. So this problem, let A be a 2 cross 2 real matrix with determinant 1, trace 3. What is the value of trace of A square? So can you solve it and give me the answer? This is a very easy problem. Again, you see this problem, again we are using the property sum equals to trace and product equals to determinant. So you see that this property we have till now we have used several times. Okay, so that's why I'm emphasizing it again and again that this is a very important property, that sum of the eigenvalue is equals to the trace of the matrix, product of the eigenvalue is equals to the determinant of the matrix. So what is the answer of this problem? We can just use this. Yeah, just find out the answer. Yes. So okay, let's do that. So if lambda 1 plus lambda 2 is what? 3, and lambda 1 times lambda 2 is what? 1. And then what we have to find out? Trace of A square. So we know that, no, inner products, that's why I'm saying 1 1. Inner products are, see, they are, that's why it depends on the field, because you see, as I'm saying, alpha xy is equals to alpha xy, but x alpha y, this is equals to alpha bar xy. Okay, but this is not bilinear thing. Bilinear means what? Whenever I have bilinear, it means that f of xy, if it is a bilinear, it means that f of alpha xy equals to alpha f of xy. Yes, but that depends. See, these two things are depend. So that's why I'm saying, see, bilinear, if I'm saying if it is on the R, then this is bilinear. Okay, if we are in the R, then this is bilinear, because bilinear means this. It is complex thing. It is like you have the complex conjugate will be coming. So it is alpha bar f. Sorry, this is alpha f x y. This is the bilinear means this, that linear in both component, but inner product on C is not linear on both component. Okay. Yes, it is. It is not. If you take the field at C, then it is not. Okay. Yeah. Right. So lambda 1 plus lambda 2 is 3 and product is 1. And what is the trace of A square? We need to find what. So what are the eigenvalues of A square? It's lambda 1 square and lambda 2 square. So this is just this. So what is this? This is lambda 1 plus lambda 2 whole square minus 2 times lambda 1 lambda 2. So this is what? This is equals to 3a square, that's 9 minus 2, that's a 7. So this is the answer. Okay, is it clear? Yeah. Okay, so this is, so I'm again saying this. So this property is very very important. Okay, so I am saying this property is very very important. Okay, yeah, but in general, sorry, what did happen? Yeah, not visible, not clear. No, I'm not. Sambe Srinivasrao. Yeah, what is not clear? And is it visible to everyone? Sambe, you can just go to. Let me just see whether my thing is. Yeah, stream is healthy. So I guess there is some. Yeah, visible. It's visible. Yes. So yeah. So Sambe Srinivas. So this is, I guess, you just have to. Yeah, in mobile settings are different, so I'm not sure. In mobile, you have to go to quality, and then I guess you have to go to some high quality or something, high picture quality or something, I guess. Or advanced, you go to advanced, change the advanced. Yeah, you have to go to advanced. You have to go to advanced, and then on the quality, you can see that 1080p is there, and you can apply that, and you can see that question not visible clear. Okay, so let me read out the question again. See, the question is that let A be a 2 cross 2 real matrix with determinant of A is 1 and trace of A is 3. What is the value of trace of A square? So, Sambe, what you can do if you are using a mobile phone, so I guess what you can do is like you go to the setting of YouTube, and then I guess if you go to the setting, there is something called quality, and under quality, there is an option called advanced. And under advanced, you can select 1080 or 720p, whatever is suitable. Okay. So what I did here, I used again this property that lambda 1 plus lambda 2 is equals to 3, lambda 1 times lambda 2 is equals to 1, and lambda 1 square plus lambda 2 square. This is what we have to find out. And so this is 7 as we find out. Okay. So see, I'm emphasizing this again that I have used this three property various times, that sum is equals to the trace, product equals to the determinant, and if lambda is an eigenvalue of a, then lambda square or lambda to the power n is an eigenvalue of a to the power n. Okay? Okay. Right. Yes. Okay. Yeah. So let's see this problem. Problem. If A and B be 2 cross 2 matrices, then which of the following is true? So it's like determinant of A plus B plus determinant of A minus B. So it's like you have to find out. So see, uh, of course, you can solve this problem by taking A equals to something A1, A2, A3, A4, and B equals to B1, B2, B3, B4. But see, I recommend you here, it's see, because you are in an exam and that has a time limit, so it's better to see, because here you can solve it, because see, A minus B is there and A plus B is there. So, so what I will do, I'll just take A as A equals to B. If I'll take A equals to B, what about the first option? This will be gone. If A equals to B, this all will be gone. Okay, so let's see. So in the first option, determinant of A plus A, that's determinant of 2 times A, but A is a 2 cross 2 matrix, so that's 4 times determinant of A. But what is the right hand side? This is equal to determinant of A plus determinant of A, so that's 2 times determinant of A, not equal. So this is false. Similarly, if you see this is 4 times, but this is 0 because this is minus, so this is 0. Again, this is 0. So the correct option will be this. This is correct. Okay. So see, because we are having A minus B, A plus B, so we can take A equals to B, or we can take A equals to minus B, because what will happen then, one of the terms will be 0 and then the computations will be much easier. As I told, we can take A and B and do the computation. But since we are in an exam, so the time will also matter. So it is better to compute it faster and faster. Okay. So is this I hope this is clear to everyone. Okay. So let's go to the next problem. Yeah. If A is this, then A to the power 20 we have to find out. Okay. See, in general, if it is a like, see, this is a 2 cross 2 matrix, so here it's not a very difficult thing to compute. It is about 20, but but here also I'll point out some important facts. But in general, when we have to compute the power, what we used to do, if A is diagonalizable, then computing the power is very easy. But you can check that this matrix is not diagonalizable. But of course, we have, as I told, this is a 2 cross 2 matrix. There are a lot of ways to compute it. So first way is just computation. So let's see the first way, which is like, if nothing comes in your mind, then we just start computing. So what is A? A square is what? 3 minus 2, 2 minus 1, 3 minus 2, 2 minus 1. So what is this? This is what? 3, 9, and minus 4 is 5. And this is, I guess, minus 6 plus 2 minus 4. I guess this is 4 and this is minus 5. And if you compute a to the power 4, so it means that you have to compute a square of this. Then this is what? This is, I guess, 5 minus 4, 4 minus 5. And what is this? 25 minus 16, 9. And I guess minus 8, 8, 9. Okay. You see that you have a pattern now. Because what is this? So this is equals to, so let me write 8 to the power 4 equals to 2 times 4 plus 1 minus 2 times 4, 2 times 4, and minus 2 times 4 plus 1. Okay. And you can check that this is indeed a correct thing, that you have a to the power n. If I have to compute a to the power n, then a to the power n is what? 2 times n minus 2 times n, 2 times n, 2 times n plus 1. So as I told, this is like if nothing works, like if you don't see anything, just do some multiplication and it won't take much time. But there are easy ways also. So first way is, again, using the property that sum of eigenvalue equals to trace. Okay. And product of eigenvalue equals to determinant. Okay. So you see that what is the row sum? Row sum equals to 1. Hence 1 is an eigenvalue. So 1 is an eigenvalue and another eigenvalue will be 1, because the trace is 2. So these are the eigenvalues. Okay. So what are the eigenvalues of a to the power 20? So eigenvalues of a to the power 20 will be 1 and 1. And hence the trace will be 2. So of course, in all the options, trace is 2. So this is not useful. Let's see the determinant. So what is the determinant of A? It's 1 times 1. So determinant of everything should be 1, because the eigenvalues is this. Okay, let's see the determinant of this. What is the determinant of this? That's 41 times minus 39 minus 40 square. But what is this? This is nothing but, it's like, if you compute, this is You don't have to multiply also here. This is 40 plus 1, and this is 1 minus 40 and plus 40 square, something like. So you just have to, and this is, you can see that this is 1 and this is 1 and these two are not 1. Sorry. Yeah, because this is like, see, uh, this minus and this plus, so this is fine. Minus plus, this is, but this is minus and this is also minus. So this is not 1, this is not 1. So 3 and 4 are wrong. And instead of, for 1 and 2, what you can do, see, so both have the determinant properties are same. But there is a beautiful property that we have seen also, that if a row sum of A is lambda, then a row sum of A to the power n is equal to the lambda to the power n. Okay, and this is very easy to show. It's again, you consider the matrix 1 1 1 1 1 and consider A to the power n, and now this is what? This is A to the power n minus 1 lambda v. This is A to the power n minus 2 lambda square v. This is again, in this way you have A lambda n v, sorry, lambda n minus 1 v, and I guess this is equals to lambda to the power n v. Okay, so you see that lambda to the power n sum, this is coming. So what will be the row sum? So since the row sum is 1, the row sum will be 1. But you see in this option, in the first, sorry, in the first option, the row sum is not 1. Okay, and hence this is the correct answer. So as I told, you can directly do the multiplication. It was much easier in this case, or you can do some like rules. Okay, but in this case, the computation was much more easier. So you don't have to go by any other rules. Okay, so let's see. Yeah, again, see the quadratic form appears into the picture. So which of the following real quadratic forms on R2 is positive definite? Okay, so we have to see which of the following real quadratic form on R2 is a positive definite. So Q is from R2 to R. Okay, so Q, as I told it, so Q, this has the property that Q of x is always greater than 0 for every x non-zero. Okay, Q has, it's a quadratic form, and this is not difficult to show because what is this? X transpose AX. Okay, this is the thing. And A is, we know that A is here is this, so this, if Q is a quadratic form, then X transpose AX is always greater than 0 for X non-zero. Because, okay, and hence what has happened? Hence, we just have to check, this property. So see, the first one is what? Q of 1 comma minus 1. If I take this, what is this? This is minus 1. This is negative, not thing, not good. Okay, and sorry, this is gray, right? And what about this? The second one we don't know. Let's see the third one. So Q of 1 comma minus 1 is 0, again false. Fourth one is also Q of 1 minus 1 is 0, again false. And hence the correct option is this. See, these are like you just, as I told, the quadratic form, just like learn the quadratic form, because each year one problem from this, the B part, and one problem in C part, the quadratic form you will see. So as soon as you learn the quadratic form, it will be easier for you to solve more problems. And they are very easy problems. It's not lengthy problem. No, Q, Oh, sorry, sorry. Yeah, you are right. And this is my mistake. Sorry, sorry. Yeah, Manmohan, you are right. Yeah, QXX is 0. Sorry. See, let me. So the thing is, uh, Q of, yeah, you are that this option is right, that Q of XY I have written wrong. Although the computation was correct. The computation was correct. The property I have written wrong. This is bigger than 0. So XY non-zero. Yeah. What for positive definite? What for positive definite? I don't understand. I don't understand your last comment. Of course, you have to check with here with 1 minus 1. That's right. So this was the thing that we have to. Oh, okay, okay. So it's QXY for positive definite. The thing, see, skew xy. So here is like this is a property of the quadratic form, that because see how the quadratic form will look like generally. It's like whenever you have a quadratic form, we can just because its main thing is that see this property q of x, because see x. So if let me write in general. So q from Rn to R, and q of x is a vector x here. Okay, this is always greater than 0 for every x non-zero. So whenever you have non-zero, this is true. Because see why, because you are computing the why, because you are doing x transpose ax. What is this? What is this? This is x with, and this thing is greater than 0. Why? Because this as a this property, you see that A. We are asked to check positive. Of course, yeah, that's why I'm checking the positive definiteness. Yeah, I'm checking the positive definiteness because this is the property of the positive definite. This is the meaning of the positive definite. Because if A, see, if Q is positive definite, this means that this A is positive definite. This means that q of x is bigger than 0 for every x non-zero. So I like I don't know, like did I made some mistake? Yeah, this is the meaning. Sorry. Oh yeah, right. I made a mistake here. Right. Yeah, thanks, man. This is like if this probably this is not always true if q is positive definite, of course. Yeah, if q is positive definite, then this is true. Right. Yeah, not always, of course. Sorry. So if Q is positive definite, then this is true. Right. Yeah, you are right. So Q positive definite implies Q x is greater than 0 for every x non-zero. This. Yeah. Yeah, you are right. Yes. We asked the positive definite. Yes, right. This. So whenever you have a positive definite quadratic forms, it means that this will happen. Okay. Yeah, sorry about that, and thanks for pointing this out. Okay. So now it is clear, Manmohan? Yeah. So please let me know if it is clear. Okay. I can proceed to the next problem. Yes, thank you. Okay. So then let's go to this problem. So it says that if A is any n cross n matrix such that the set of all non-zero eigenvalues of A has exactly R elements, then which of the following statement is true? So what is given? That lambda non-zero such that A lambda, sorry, AV equals to lambda V for some non-zero V. Okay, for some non-zero V. And this cardinality equals to R. So A is an n cross n matrix such that the set of all non-zero eigenvalues has exactly R elements. Okay, and non-zero things. And then which of the following? So see, non-zero eigenvalue has exactly R elements. So it means that rank will be what? At least R. So rank is bigger than R. So this is bigger than equals to R. So this means this is false, this is true. Okay. See, since this is I guess this is a single option. So since this is a single option correct, we can directly stop it here. Okay, but just for the sake of completion, let's see that this option and this option are false. Because see, why this option, the second option? Because it says that less than n minus 1. But see, like if R is equals to 0, it means that all the eigenvalues are 0. But this does not imply that, because see, rank of A is less than n minus 1, but rank of A could be n minus 1 also. For example, you just consider 0, 1, 0, 0, this matrix. What is so here R equals to 0, but you see what is rank? Rank equals to 1. But this is not n, this is not less than 2 minus 1, this is not less than 1. So this option is wrong. And A square has R distinct eigenvalues. This is also false, because if let's say 1 minus 1, 0, 0. So A has two distinct eigenvalues, 1 minus 1, but A square has only one eigenvalue, distinct eigenvalue, that's 1. So this option is also false. And therefore the correct option that we are already obtained, the third option. Okay. So yeah. Okay. So again, see, the problem of inner product came, like whether P is an inner product or not. Okay. So what is the problem? For AB in R, that Pxy is this plus this plus this. And then we have to see for what values of A and B, P defines an inner product. Okay. So for inner product, what I told, that X transpose AX. And this has to be symmetric positive definite. So let's write down the matrix A here. So what is the matrix A? It's A square, AB, AB, B square. Okay. What is the determinant of A? So the determinant of A equals to A square B square minus A square B square, which is 0. So determinant of A is 0. So hence A cannot be a positive definite matrix, and therefore whatever A or B you take, this cannot be an inner product. So this is never be an inner product. Never be an inner product. And therefore for all values of A and B, you can't find any value of A and B so that it is an inner product. Okay, right. So yeah, so now part C. So I'll I'll stop here. Uh, so yeah, so if you have any question, we can proceed with the questions. And in the next session, that will be on Sunday. So next session will be on Sunday, and we will talk. So the aim of that session. So aim will be we'll solve June 2020 We'll try to solve the November or December 2019 linear algebra problems. Okay. So in the next session, that will be on this Sunday. So I guess today is what? 26, 7, 8, 9, 10, 30. So on 30th April. So on 30th April, we'll have our next session, and there we'll be solving problems from June 2020 and November, December 2019. And yeah, so since like this was my first what is the streaming, I haven't streamed before, so I have linked a feedback form in the description. There is a feedback form in the description, so kindly fill it so that I can improve more. And yeah, some of you have asked in the WhatsApp whether it's free or not. So yeah, it's always this is always free. So I'm not going to charge anything. This is always free. So yeah, and in the description you can see uh, I have the WhatsApp group link is there, so you can join the group. And there is a feedback form, as I told, that is for my improvement. Of course, I have to improve a lot uh, to make it clear to you guys, because it may be clear to me, but it may not be clear to you. So, if you can write in the feedback so that I can improve in the next section, I'll try to improve on those points. And the third is there is a Google form uh, for email collection. So I'll just whatever the schedule will be there. Either you join the WhatsApp or you can fill this Google form so that I would have your WhatsApp detail or I have your email detail so that I can send any notification on any uh, session detail on that link. So if you have any question, you can ask. Uh, Otherwise, we can end the session. So, thanks all for your time. Please fill out the feedback form. Okay. So, if you have any question, now we can proceed with the questions. So, I'll be here more 5 or 10 minutes. Yeah. Thanks, Manmohan. Thank you, Sambe. Yeah. Please feel please fill the feedback, because I think the improvement is needed in my end also. Thank you, JSED. Thank you, Abhirup. Okay. Yeah. Thank you, Sujata. And if you like, apart from this session, if you need some other session, please write in the feedback form so that I can plan accordingly. And from next week, it will be on Saturday and Sunday, the same timing, 3 to 6. So from next week onward, it will be Saturday and Sunday from 3 to 6. Okay. Yeah. So if you have any question, we can proceed with the question. So I hope you don't have any questions. So I'll just, yeah. So you have any questions, please let me know. Or, and yeah, and there are like, I used to uh, give daily problems. So you can solve these daily problems. Sorry, this is not. Um, so you can solve these daily problems. So these daily problems like contains all, like I used to give one problem regularly on Sunday, starting from linear algebra, then real analysis, then complex analysis. So if you'll go to the website and you see there is a calendar. So today I have not given the problem. I was busy with this. So if you, I'll just, what I will do, I'll just, I'll just, yes. Well, yes. So you can see that this is the daily problem thing. So what from January 1, you can see like if you go to January 1, there's a problem on uh, this the linear algebra. So on each Sunday, you'll see a problem on linear algebra. On each, so this is the schedule. Sunday is linear algebra. Monday it's real analysis. Tuesday it's complex analysis. Wednesday it's abstract algebra. Thursday it's topology. Friday it's differential equation. And Saturday it's arbitrary. Okay. So and you can get the problems from this calendar. So you can go to the dates, corresponding date, and you'll see the problems. And the solution is also written. Usually what I used to do, I provide the solution on the next day. So this is the like the problem thing. Okay. So yeah, so keep doing problems and thank you for your like patience and the time. We'll meet on Sunday. Goodbye. Take care.